thank you for staying. It's quite late now, and also it was an amazing talk, the one before, so I hope I can keep you entertained after this one. So what we are going to talk about is how to understand these foundation models that we have right now. And it will be mostly vision, so the talk is mostly vision, so it's not all the foundation models. And we're going to talk about two specific perspectives, evaluation and interpretation. So usually when we talk about understanding, it's always about explainability. So yeah, so just let's start with one of the famous benchmarks. So for vision language models, so the paradigms have changed, right? In computer vision, we had a model trained on ImageNet, on classification tasks, and you just measure the accuracy. And there was not much else. Now you pre-train a large model on a variety of data just via, I don't know, self-supervised learning or just auto-regressive, anything. That's kind of could be considered also self-supervised, but you just pre-train and then you have different tasks. So how do we evaluate these models? So for example, like the visual language ones, like this is one of the famous benchmarks which evaluates a visual language model on, for example, counting tasks. And as we know, these models are not good at counting, so if you like ask how many objects of this specific thing is there, it wouldn't work well. Also OCR, which now researchers are trying to like adopt methods to understand how to make these ones better. So this is like the new paradigm of understanding, that's evaluation. Now there is this famous recent work, like maybe 2 months ago, from actually Jan LeCoultre, who was maybe a little bit criticized today, but in vision he has some nice ideas. So we know that these visual language models, for example, Blip, Lava, whatever, they're using a clip vision encoder. And now the current vision language models are quite hacky. You have a vision encoder, you have an LLM, you just connect them to each other. It's like having a person who sees, talks to a blind person, and the blind person tries to describe to you. So it's very hacky in this way. And what the other guy sees is also quite impaired, so as if you have a clip vision encoder. And this paper shows this, like finds 10 different categories that shows these models fail, like small objects, when the objects are occluded, when the perspective changes, when there's rotation change. And they do a complete analysis on all these marginal cases where the models are failing. And they pinpoint to the fact that it's because the clip vision encoder is basically not rich enough. So clip is trained by language supervision. And they show that the model like Dino, which is self-supervised only vision, would actually have, it's also known as a little bit in computer vision, that has higher and like richer visual features. So Dino and so. So it would be the next phase of, let's say, VLMs, where you have probably self-supervised vision models, and you want to like do the reasoning in a higher bandwidth of vision rather than having a vision one that's connected to an LLM and you do the processing sequentially. So this work is like one of the recent ones, which is getting citations quite fast. So like people are moving in this direction. And of course, there are other ways to evaluate these models. And like this was one of the fun papers, Breaking Common Sense. It's called the Whoops data set. Actually, it was this year ICCV. So they create data sets that kind of you manipulate the image in such that instead of having a bear catching a salmon, you have a panda. And you try to evaluate how this model works in these VIA settings and try to see if it actually understands. So again, since these models are hacky, you have a vision model which gives some tokens and the language model needs to save it from those tokens. Since the language model has a certain common sense in it, it would kind of be wrong in these models. So at least for the first generation VLMs, it was not working well. Now GPT-4 is working well on this, but it could be that we don't know what's the implementation behind GPT-4. It could be that there are multiple models that are first detecting everything, then you ground the language model on these detections, rather than having an end-to-end visual language system. Another interesting evaluation for these vision language ones was this equivariant similarity one, which it creates cases where something minimal changes in the image, but the semantics change overall. And for vision models at the moment, like clip ones, the embeddings for these images would be the same. So they would consider these images as the same. And something like Dino again or IGEPA, I don't know if you have heard, would work better in these images. So again, another case for going through self-supervised learning on vision data only. And another very interesting work again, so to understand how, again, these foundation models are working, is that this paper is only working on LLMs and tries to understand if LLMs understand vision. And to some extent, they do, to some basic tasks. For example, here, you just generated these images using LLMs, and you train a resonant model on these, and this actually works out of distribution data. But this, again, like it's to say that with language alone you get a basic understanding of vision. Of course, there are many cases where there is no visual thinking, and it's also would be a nice research direction for future to try to define vision tasks which LLMs would naturally not be able to solve, and would provide the case for going like multimodal in a pure way, not this hacky way of connecting things together. And so another paper which does analysis to understand was this: does a clip model know about a red circle? And what was done here was that you see if you just draw a red circle on the clip trained model, the attention moves there, and the model would if you the input through the text encoder something similar to something relevant to that point that you're pointing, it would be the highest probability. So this was quite interesting that something like this emerged from training, but of course there is discussion that this could be that there are red circles in the data set and the model has been actually seen this already, and that's why a red circle works. So we try to kind of test this hypothesis also by optimizing for the prompt that actually guides the attention. And we see actually like one of the optimal points for like a clip model with a width large would be actually via optimization we find the red circle as something optimal that guides the attention. But of course you would also can find other colors that would even get better results. So it is not strictly that since there's a red circle now the model is only working on red circle. It has learned some compositionality in colors and circles, so it would understand that the circle is actually pushing the model, is telling you that to look here, but also other colors would work as well, and with also minor noises inside. But with models which are like totally self-supervised, like Dino V2, something like this has not emerged. And it is interesting. It says that again, like in the data set, whenever there was a circle or a box, there was probably the annotation was regarding that area. So this emergence happened because of that. So this is like another way that we are understanding how these models are forming behaviors by just looking at forming certain behaviors by just looking at them in different setups. And this paper was one of the top papers like in Europe this year, which was kind of criticizing the fact that we say emergence and so, from the sense that they are unpredictable. And they actually show that our metrics are failing at the moment, which again is an argument that this evaluation direction is actually quite a promising direction to move forward to understand the models. They show that since our metrics are not continuous enough, you suddenly see something that you haven't seen emerge. But if you actually do continuous testing, you would see that this emergence is gradual by data. And there are like works on top of this that actually that discuss this. And another direction within, again, BLM evaluation is hallucinations. And there is this famous Pope dataset. Of course, there are much better datasets right now to detect this. But as you can see, like if you have an image like this, they try to test the model in 3 different settings. Like, is the random, popular, and adversarial? So, for example, in the random one, they ask if is there a random object, a bottle in the image. And in the adversarial setting, they ask something that's actually relevant to the picture. Is there a pair in the image? And the models usually say yes. And this again, like these data sets are actually to show you, to measure that how much visual grounding is there in the image, which, as we know, based on the structure of what the VLMs are at the moment, they are not well grounded. And we do also something similar with these type of data sets to try to see if there is texture versus shape bias. So for you, all of you, I guess, see what the object, what the shape that's actually very salient in this picture is. But a vision language model would not understand this shape. It would just describe you the scene, that there is a village, people there, and trees. And again, like, we do this by evaluation to show that, okay, there is still a gap for understanding shape. So we are having a workshop on this types of evaluations for VLMs in upcoming ECCV. And if you have works related to this, please consider joining or submitting to our workshop. Of course, we have amazing speakers, especially Toralba, Sainji, and Philippe Isola, who are working directly on this topic at the moment. So we have these guys, and I hope if anybody's working on this actually considers this. Now we get to the second line of evaluations, which was interpretation, looking into the models, which is something that I was mostly doing for my PhD. And from the evaluations, you look at the behavior from outside, interpretation, you look inside the model. And something that I did extensively in the old days was interpretation for local explanations. So there is some terminology here, like explanation versus interpretation. Usually it's used interchangeably, but for the sake of argument, let's now say that for explanation you are trying to describe the rationale behind an output that was generated given a certain input. So you are looking at the local space. You're looking at the input and what happens, and try to explain the output based on that input. And one of the main paradigms for this, like until like 2 years ago before the paradigm changed, was feature attribution. And feature attribution basically is, if you're given an image network output, what parts of the image were responsible for that output. It's a very hard problem to solve, maybe like around, let's say based on the papers with the most citations, 20,000. Then you could estimate like around 30,000 works published from 2016 afterwards on this topic. And the problem is still not solved. And we were trying to solve this for just basic ImageNet models, and then suddenly you have these huge models, and then there is no way to actually solve it anymore. And these are the famous feature attribution methods, which some of them, like RADCAM, you might have heard and used a lot in the old days. And there is this phenomena that if you have multiple feature attribution methods, each of them will generate different results, so you don't know which explanation is correct. And this is still an open research problem called the disagreement problem. And faithfulness, which is if the explanation is actually faithful, is it actually explaining the model? And these are still open. This would be useful if you kind of solve it for current systems as well. It has its own applications. Is that if you have a model making a certain decision on a legal case, why did it make it? So if something goes wrong, we can actually try to see who's responsible for this. But still the problem is not solved, and we have tried to make it solvable by putting evaluations for feature attributions. Of course, there are like 100 evaluation methods as well. This was our idea, that we actually generate a data set. So in computer vision, we generate a data set where we know what feature is causing what. So when we know what feature is causing what, if there is an explanation afterwards, like this kind of things, we try to match them with the data set to understand, the ground truths to understand which attribution method is doing correctly. And this was 2022, and then suddenly the paradigm changed, and we were like, okay, what do we do now that nothing is solved? Do we go bigger? What do we do? We actually did the inverse. We went smaller. So this time we actually make a really small network and a synthetic data. So we know everything in this setup. We know if this network gets this input, why it's saying that there are 500 pixels of red pixels in this image. So if there is an explanation telling you why the network said that, we can test it to see if the explanation is correct. So this is still an open research problem. We can say what method is wrong, but we can't say still why, and we cannot say still if there is a solution that actually would be the optimal one. So this feature attribution research is still open, and if we solve it at some point, it will be useful to actually understand bigger models at their point of decision making on a specific input given. So this is one direction within interpretation. The main one at the moment, like the mainstream one, which gained a lot of interest in the past year, let's say, is something called semantic interpretation and also mechanistic interpretation, which you might have heard the mechanistic one, the buzzword, a lot these days, especially by Anthropic, which is a new company focusing on explainability, interpretability. And so what is semantic interpretation? It actually goes way back, and of course could go to neuroscience, that you want to understand what neurons correspond to in terms of features. But let's say one of the first works was this in this saliency maps work, deep inside convolutional neural networks, which in one section they also do semantic interpretation. That is, they try to understand if you optimize an input to activate a certain output, what would happen. And for example, if you have a network that has a COP output, if you try to generate an input via optimization that maximizes the COP output, what would happen? And this was the early days, and this was again another work in the early days that you see what maximizes each filter or neuron in different layers. And then it just got more advanced via more advanced feature visualizations, and you can see like the hierarchical representations that are forming in the networks, from edges to more complex shapes. And again, like another one within the same direction of trying to understand what happens, semantics are correspondent to each neuron, was this network dissection work, which you go through a data set, you see what images activate a certain neuron. So a certain neuron might be activated by a house, another one might be always activated by a dog. And this was another semantic interpretation work. Now, what happens in the new days, so this is again recent, so those were all old papers of semantic interpretation. This is a new one from like 2 months ago, which you do the same semantic interpretation on a clip, and you try to understand what each attention head corresponds to by going through the data set and seeing the corresponding text, embedding, and doing a linear decomposition to like understand what each head is doing. It's an approximation, but you would understand, for example, that, I don't know, layer 22, head 1 is a shape head. And this type of interpretation is actually useful to understand how the semantics are formed and what's happening inside the models. And of course, there is a lot of drawbacks to these types of interpretation too. They are prone to confirmation bias. We are just seeing what we are looking for, so then we confirm our hypothesis. But still, it gives us an intuition what's happening. And this thing actually is called probing let's say in interpretability literature, that you actually probe a model to understand if the certain neuron or a certain layer corresponds to a certain concept. You put a classifier on top of it. We did this same probing for a safety kind of work as well on diffusion models. So right now, if you just I don't know, use any ChatGPT, Bing, and so. For safety, what they do is they have a language model apparently on top that checks if there's anything unsafe or if it looks adversarial or so. It's a little bit time consuming and a lot of times actually generates. You can easily bypass it. We just propose a very simple architecture to stop this. That is, we just put a probing classifier, contrastive probing classifier in the text encoder. It's a very easy and hacky method, but it works quite well. And for deploying on image generation methods, it could be actually very useful to stop making unsafe content. And of course, there might be some inappropriate images on the left, but we just show that this type of specific simple contrastive probing, that is that you put a classifier in the neuron levels. In the neural level, in the text encoder, could actually stop a lot of harmful things, getting from adversarial tokens to rewordings, like if you explain something with different words, to explicit statements, those tokens. So Yeah, this was a tangent to how probing from interpretability literature can actually help with safety. So this thing was semantic interpretation, that is, you try to assign semantics to neurons and layers. Now what is mechanistic? Mechanistic one is actually mostly in NLP domain right now. In language models, it's quite hot. There are many works, maybe 50, let's say, per month are coming up. But for vision, there are not much, and you could maybe just find this one from 2020, which kind of started. This paper was from Chris Oda, which is the founder of Anthropic, who is now pushing mostly for mechanistic interpretability. And what is mechanistic interpretability? It's that you try to reverse engineer the algorithm of a model. You try to understand what is the inner algorithm of doing things. So if you're detecting a car, how are you detecting a car? And it's a very experimental work. You try to go to different neurons and filters, and you understand, okay, like window, car, wheel, they all kind of go into the next neuron, and they do a car detector. And there are many new works in the language domain. There is a lot of open space in the vision one, which all of these works could be adapted to vision. And I will show you just one which came out 2 days ago as the last slide, as kind of an automated interpretation. And what they're doing is that so this is kind of, let's say, the only good one in computer vision right now that actually is doing this kind of automated implementation. And what they're doing is you have a agent model similar to Whisprog or Viper GPT, which actually writes code for you. And you would use all of the things that we discussed earlier, how to like semantically assign concepts to neurons. And you, for example, with the first blog, is showing an example of how the model is writing code to use some inputs in the data set to see which one activates a certain neuron most, which parts of it, and then you generate some hypotheses using an LLM. Okay, this might be, for example, in the first image that it's a bow tie detector. It could be a bow tie detector in a fancy environment. It could be just in any environment, and you generate data for all of these, and you test the hypothesis. And this way you can automatically assign each neuron concept why it's activated. And then you can also see if it's actually a causal, it causally also exists, that if you remove that neuron, if you do this intervention, also that concept, that model's detection of that concept kind of is hurt or not. And yeah, this is something like you automatically do all of these early works that we discussed about semantic interpretation into one model. And of course, the future, you can also do this mechanistically, try to understand what circuits exist in the model, now that you can actually automate it in an automated way to analyze everything in the network. So yeah, I tried to speak, I guess I spoke really fast, and this was the final slide. So if you have any questions, just let me know. Thank you.
Questions?
Sorry, that was a lot of information. Can you just repeat the main topics you are involved in again?
So it was understanding in terms of evaluations and interpretation. I wanted to go slower, but it was not time limit. But yes, so it was the main topics were one direction was one thread was evaluation methods that we're talking about, and one thread was looking into the model and the interpretation. So I just want to give an overview what exists, what would be the current research in each of these, and what we can.
Okay, maybe I can ask one question.
Yes. Sure.
So what do we expect if a large model can count objects? What could be the next thing? Let's say. Mm-hmm. So okay, counting could be a sign of more emergence, right? So that it can start to understand more from the environment or from the data it's trained on. What's the, let's say, what would be the next steps towards? I guess it goes towards general AI, right? Mm-hmm. What would be the next step then?
So for now we are just understanding that this certain thing has not emerged by this the specific tasks that we are having, and then we could understand why. We could go into the model and understand why this is happening. So it seems to be, at least for the clip-ons, it seems to be happening that you just generate a token that something is existing here and here, and then the language model could ignore this and just say, okay, this is existing here, and not keep count of all the things there. And we can go one step ahead and fix this. Or you could try to see what, if we include a lot of count in the data set, would it be solved just by, I don't know, automatic masking or so? So it's just giving us hints that something is wrong, what needs to be done next to actually fix this. And yeah, this is just, as I said, it's just trying to understand and then moving forward to that. I wouldn't be able to say what's next, but it's just telling us that there is something that needs to be done to be the next thing.
Yeah.
Yeah.
So what do you think when I would say to have general AI? It's maybe not the right way to use just a data set and train on a specific loss, but maybe to I'm asking for your opinion, right? Maybe to play a game which is like very rich of, maybe reflects our world quite well, and to survive in this game, let's say. Could this be, let's say, one interesting approach?
So, whatever I would say, like, it would be kind of parroting the other people's opinion, of course. Of course, in the end, if you have a model which could interact in the world and the loss is to predict everything, then I guess if you can solve it, this is one of the ultimate loss models. The thing is, we can't at the moment. But of course, it's a great loss model because in order to interact and do everything, you need to actually know everything. So you need to have a world model. But for the simple cases at the moment, for the vision part to actually be solved, this is again, I'm just parroting this Jan de Koon's opinions, let's say. It seems one major advance that's happening is this joint representation. So Dyno is basically just kind of like a masked autoencoder, let's say, like in terms of training. It's a self-supervised language if you're trying to train. And now you do this in the embedding space with two inputs, each one having something masked in the input, and you try and match them. And this seems to be working really well in terms of like having few data and having like a good visual representation. And this seems to be like the latest kind of trends that I'm aware of in vision, and the later one being the same thing for video, VGPA. I don't know if there are like some video people could correct me if it's actually the best at the moment or not, but at least it seems to be one of the ones that's actually working really well with few data. So yeah, this is what would I know, like in terms of loss, that's actually working well at the moment for vision.
Thanks.
Just
a quick question on that work that you were doing regarding the attention on the very simple model. Like, what were the conclusions from that study that you did on simulation with very simple features to try to understand which of the metrics is better to understand, like where the model pays attention to?
So the conclusions was that, so there are many different attribution methods. Like we could see like the class of methods that were trying to approximate the Shapley value, which is a very axiomatically defined way to define contribution. Those approximations in certain conditions would work very well, and that was like the main conclusion that actually this is one way to go. But of course there are issues with approximating Shapley value. It's very computationally expensive, and certain approximations could actually go very wrong in real cases. So it just points to the fact that research needs to be done in that regard, and at least for now, in what settings should be used feature attribution methods to actually have the right explanation.
Yeah, thank you. Well, thanks, Dr. Ashkan. And Vivo technology help supply the best paper reward, and let's welcome One help to announce who achieved the presenter 2 awards.
Yeah, hello everyone. I'm Onay from Vivo, and on behalf of Vivo, which is also partly funding this event. It's my honor to announce the Best Paper Awards. There is the Best Paper Award and a Best Paper Runner-Up Award. So I would start with the Best Paper Runner-Up, which goes to Yongshuo Zong on safety fine-tuning at almost no cost, a baseline for vision large language models. Congratulations.
Thanks.
And finally, the Best Paper Award goes to Jianing Huang, Open Inst 3D, Snap and Lookup for 3D Open Vocabulary Instance Segmentation.
Okay, and I think that's everything for today's. And thanks for everybody come for today to join our meeting. And that's it.
Thank you.